Well, welcome. In this video, we're going to be looking at lesson 3.7. Now, in this section, we are now concluding this chapter all about polynomials. And in this one particularly, we're going to be looking at how to identify whether a polynomial is an odd or an even function. And so we're going to be looking at some different symmetry of those functions. And so we're going to skip the warm-up for this lesson, for this video. So we're going to step right into this idea of odd versus even functions. So as far as all of this in your notes, I would just say focus on what I will be highlighting, or I've already highlighted here. So how do we identify an even function? An even function is when we have a function that's symmetric about the y-axis. Now, we're going to be looking at how to identify whether they're even or odd functions by looking at just the graph and by also looking at just a function. But to start out with, we're going to be looking at just the graph. And to identify if it's an even function, we want to look to see if it's symmetrical about the y-axis, so the vertical axis. If we can flip it over the y-axis and it's the same on both sides, then we say that it's an even function. Now, it's an odd function if it's symmetric about the origin, not flipping it over the x-axis. It's rotating 180 degrees about the origin is what we say, using basically the origin as a pivot point. And other types of functions can also be classified as odd or even. For example, the absolute value function would be an example of an even function. So if you think about the absolute value of x, if we think about that function, that v is symmetrical about the y-axis. If you flip it over the y-axis, it's the same on both sides. So y equals absolute value of x is what we would call a even function. But let's look at what the graphs of these would look like. So here's a graph of an even function. And so again, I would make sure you get this in your notes. So let's highlight this. I would sketch a graph of that. It doesn't have to be perfect, but I would sketch a graph of that illustrating what we're showing here. And what that graph is showing us is that basically you just reflect it over the y-axis, you have the same points, they match up, so it's an even function. Now write down what's at the bottom there. So that we're not really going to, it doesn't really come into play too much yet, but what that's saying in the bottom there is if you have negative x, if you put that in the function, it's going to be equal to f of x. So write all that down, pause the video if you need to. Let's look at an odd function, what that looks like. So again, write down odd function, sketch a graph of what that looks like, and write down what we have there at the bottom, that f of negative x equals the opposite of f of x. Again, that'll come into play more when we look at an equation and identify if an equation represents odd or even without seeing what the graph looks like. But this one is almost like a pinwheel, where if you take the origin, the coordinate 0, 0, and take the graph and rotate it 180 degrees around that point, if you get the same graph, then you know it's a odd function. Or another way to look at it is if you take your paper and flip it upside down, if it looks the same as what it does right side up, again, about the origin, that's the key. It has to be about the origin that you rotate it. Then it is an odd function. Let's look at an example. Well, actually, let's look at, this is an example of neither. So this one you might say, well, this is one where if you took your sheet and rotated it upside down, it would look the same. But the problem is it's not spinning around the origin. So that's where you got to be careful with that. So you got to think about it almost like a pinwheel. Like if you spin a pinwheel, it's going to be the same as you rotate it 180 degrees. And that's the same thing here. Okay, so with this last example, this is neither odd nor even. It's not, if we reflect that over the y-axis, it's not going to be the same either way. And if we rotated it around the origin 180 degrees, it's not going to be the same graph. But let's look at another example. So here, we're going to determine whether or not this graph represents an odd or even function. So let's think about it first. If we reflect this over the y-axis, if we reflect it over the y-axis, it would look like this. So what's in blue would be the reflection. That's clearly not the same graph. Okay, so it's a brand new graph. It's not the same graph, so this is not an even function. Now let's look to see what happens when we rotate that 180 degrees about the origin. If we rotate it 180 degrees, it's going to be the same graph. It's going to look identical. So this is the same graph, so that means this is an odd function. You can also test points to confirm it, because a point 1, 1 is the same as a coordinate negative 1, negative 1. So again, the function is odd. Let's look at this one. Okay, we're going to classify this one as either even, odd, or neither. Now if we reflect it over the y-axis, it's the same graph. So that looks like it's even. Or we could test points, like if you use the point 1, 2, it's the same as the opposite of x and 2. Okay, so that's what the things at the bottom we're saying, but if we're going to be visual, we really don't need to have that test point. As long as you can reflect it over the y-axis and it's the same, you're good. You don't have to use a test point. Now, let's look at this one. Is this one odd, even, or neither? So if we reflect it over the y-axis, it's obviously not the same. But I want to talk about what's in that common error. So to make sure that you understand what the common error is, the top part of that paragraph, that's the common error. The common error says an odd degree polynomial function may have rotational symmetry around a point other than 0, 0. That is wrong. Okay, that is the common error. It is only, so what's highlighted there is what's really true. It's only an odd function if the symmetry is around the origin. Okay, so what's highlighted there is the true statement. What's not highlighted is the false statement. So you want to make sure that you understand that. It must be rotated about the origin to be an odd function. So if reflected over the y-axis, like I said, it's not the same. It's a new graph, so it's not even. If we rotate it around the origin, we would get the green graph, and that's a new graph, so that's not odd. It doesn't match up. It's not the same as what was before. So if you use test points, again, it's not going to be either or odd. All right, so I want you to test that for this one. I want you to determine whether or not this graph is an even function or an odd function, and why it is. So why don't you guys go ahead and pause the video and hit play, ready to check to see if you've done this correctly. All right, what did you get? Hopefully you got that if reflected over the y-axis, it's not the same graph, so it is not an even function. But hopefully you understood, or you saw that if you rotated this about the origin, it would be the same graph. And so this is an odd function. Okay, now I want you to try this one. So classify this polynomial function as even or odd, again, based on the graph. So I want you to see if you can figure out which one. So go ahead, it doesn't take long, but pause the video if you need to, and hit play when you're ready to check to see if you did it correctly. But you probably didn't even need to do that because you should have recognized right away if you reflect that over the y-axis, it's the same graph. So this is an even function. If you reflect it about the origin, 180 degrees, it's a new graph, so it's not odd. Okay, so the function has to be an even function. Okay, what if we don't have a graph? What if we just have an equation like 4x to the fourth plus 5? We want to figure out whether or not it's an even or odd function. Now, I don't want you to make the mistake of thinking just because it has an even degree polynomial that it's an even function, or if it is an odd degree polynomial, it's an odd function, because that does not work 100% of the time. It must work 100% of the time for it to be a trick that we can use. So this is the only trick that works, and that's this. Remember we said at the beginning, at the very first graph underneath those graphs, we said if f of negative x equals f of x, it's an even function. And if f of negative x equals the opposite of f of x, it's an odd function. Okay, that's how you can tell the difference between the two. So here's what you're going to do. You're going to put negative x into the function. You're going to see what happens. One of three things is going to happen. It's either after you put negative x in there and simplify it, it's going to your answer is either going to look identical to the original function, so it's the same, it didn't change. And if that happens, it's an even function. Second thing could happen. If you put negative x in there and you get the complete opposite of the original function, like let's say the first term was positive and then you put negative in there and it becomes negative, and the second term was negative, and when you put negative x in there you got a positive, so now it looks the same except for the opposite signs. That's how you know it's an odd function. If it's the opposite of everything from what we had at the beginning, then it would be an odd function. If you put negative x in there and some things stay the same and some things change, some terms change, then it's neither. So either both terms have to stay the same or both terms have to change for it to be even or odd. But if one or two of them change and the others stay the same, then it's neither. Okay, so let's see what happens in this one. Obviously you can see it on the screen right now, but if we put negative x in there for x, we'd have negative x to the fourth power. Now negative x to the fourth power is x to the fourth power. Times 4 would give us 4x to the fourth, and then the plus 5 would stay the same. So when we put negative x in there, we got 4x to the fourth plus 5, which is the same as what we had originally. So that tells us that it is an even function. So let's look at the next one. So again, here we have 2x cubed plus 3x. So we want to put negative x in there and see what happens again, even though you think you know that, oh, it's an odd degree and my answer is probably going to be odd. That only happens most of the time, but not all the time. So you cannot use that trick. Okay, so what we're going to do, though, is like I said in the previous one, we're going to put negative x in there. So every time we see an x, we're going to replace it with negative x and then simplify it. Negative x, when you cube it, becomes a negative x cubed. Times 2 is negative 2x cubed. So the first term becomes negative 2x cubed. The second term, 3 times negative x, would become negative 3x. So we end up getting negative 2x cubed minus 3x, which, if you notice, is the opposite of what we had at the beginning. By the way, if you do this step here, or if you don't do that step, it's not necessary. If you wanted to, you could just stop here and recognize that the 2x cubed changed to be negative 2x cubed, the 3x changed to be a negative 3x. So both of the original terms changed to be the opposite of what they were. So if they change to be the opposite of what they were, it is an odd function. All right, now I want you to try it with these two problems. So here we have 7x to the fifth minus 2x squared plus 4 and x to the 6 minus 2. So I want you to test it. Again, the only way that you can test this is using a negative x, putting it in there for x. So go ahead and pause the video and try that for both of these problems and see what you get. And hit play when you're ready to check to see if you've done it correctly. All right, how did you do? So for this first one, you should have got, when you put negative x in there, you should have got negative 7x to the fifth. Now negative x squared, when you square negative x squared, that's positive x squared. So times negative 2 would still be negative 2x squared, and the plus 4, that doesn't change. So if you notice, the 7x to the fifth, that changed to be negative 7x to the fifth. The minus 2x squared, though, stayed as a minus 2x squared. The 4 stayed as a plus 4. So one term changed, the other two stayed the same, so this one's neither. So this is where, again, you can't just look at the degree of the polynomial and say that, oh, the degree is 5, so this one must be an odd degree. This is an odd function. Doesn't work. Doesn't always work that way. All right, let's look at the next one. So that one, when you put negative x in there for x, we'd have negative x to the 6th power. Now, any negative number raised to an even exponent is always positive. So negative x to the 6th, since 6 is an even exponent, would simplify to be a positive x to the 6th. And then minus 2 would stay the same. So we have x to the 6th, that stayed x to the 6th. We add minus 2, it stayed minus 2. So they both terms stayed the same. So your answer would be this is an even function. All right, let's look at one last example here. So we're going to look at what happens to the graph of these functions, of cubic and quartic parent functions. So here we have 3x to the 4th minus 18. Now, 3x to the 4th minus 18 is based on the parent function x to the 4th. All right, so we're going to tie everything that we've been learning in this chapter. The fact that it's the leading coefficient there is 3, it's going to stretch the graph vertically to be 3 times the size. Okay, making it narrower than the original parent function. Because if you stretch it out 3 times the size, remember the picture gets narrower. An easy way to remember that is if you have a picture, like if you're creating a PowerPoint and you paste a picture in there, but all you do is if you resize it by just grabbing if you click on the image and you just click on the top square and drag it, it's going to stretch it out vertically. And what happens is it makes the picture look skinnier than what it was originally. So that's what happens. If we stretch something out vertically, it makes it skinnier or narrower. And so that's why right now the red graph there would be the 3x to the 4th part. Now, subtracting 18 means it's going to move the graph down 18 units. And so what's in green now would be the final 3x to the 4th minus 18. So that's how you can combine some of these transformations to the graph. So let's look at this one. And here it says, how does a transform graph compare to the graph of the parent function? So in this graph, we have 5 times the quantity x minus 2 cubed plus 4. So the transformations here are the minus, we have a 5 out in front, we have a minus 2, and then we have a plus 4. And all of that is based on the original parent function x cubed. So what's there in the graph above me here in blue, that's the parent function. Okay, so we're going to look to see how is a parent function going to be affected by these transformations. So we can do this in any order. Okay, the minus 2 means the graph is going to move to the right 2 units. Remember that from earlier, much earlier. So x in parentheses minus 2 means it's going to move to the right 2 units. So what's in red now would be our new location for the graph. Okay, now we have the 5. The 5 is going to stretch it out vertically to be 5 times the size vertically, which is going to narrow the graph. So that's what's in green. And then the plus 4 means that it's going to move, we're going to move that graph up 4 units. So what's in purple is your final graph. But the way that we describe what happened here is it moved, translated to the right 2 units, up 4 units, and stretched vertically 5 times the size. So that's how you could describe it in words. Okay, so I want you to try this one on your own. So I want you to, in your own words, describe the different transformations that are happening with this function compared to its parent function. So go ahead and pause the video, write those out. Be detailed with how you write those out, but write those out as far as what's happening compared to the parent function, y equals x cubed. So then hit play when you're ready to check to see if you've described that correctly. All right, let's see how you did. Should have said something like this. And again, if you said it in a different order, it's totally fine. So here this graph would be translated down 5 units, and the 2 in front of there means that it would stretched vertically to be twice the size. Well, there we go. That is the end of this video. So hopefully you understand now how to translate these graphs and how to determine whether or not a graph, a polynomial, is odd or even or neither based on the graph and the equation.